Good evening to all who are watching this webinar in YouTube Live. I thank our Honorable President, Sir Engineer ACS Arun Kumar, and the management, Dr. MGR Educational and Research Institute, for supporting the Mechanical Department for first year campus to conduct this webinar during the pandemic time. Now I call upon Dr. Bindu, Department of Civil Engineering, to give a welcome address.
Of Mechanical Department, first year BTech, Dr. India Educational and Research Institute, Chennai. I would like to extend a very warm welcome to our Vice Chancellor, JR Sir, Dr. Subhashri Madam, Dean E&S. Welcome you, ma'am. I take this opportunity to welcome our speaker, Dr. Divya Panchanathan, Senior Research Engineer at Donaldson Company, USA. Welcome you, ma'am. I extend my warm welcome to faculty members, students from various colleges, universities, and other participants to this webinar on Engineering Smart Surfaces for Anti-Fouling, Hydrophobicity and Drag Reduction. Hope this webinar is going to be interesting, informative, and knowledge sharing for everyone. I also thank you for taking time out from your schedule and joining us for this webinar, accessing through video. Thank you, and once again, I welcome you all for this wonderful webinar.
Thank you, ma'am. Now I welcome our beloved Dean, E&S, Dr. N.S. Subhasti, give you a special address.
Thank you, Mr. Saravanan. Hope I'm audible to all.
Yeah, ma'am.
So, as mentioned, during this pandemic time, we are all connected virtually through such webinars. And this Department of Mechanical and Civil Engineering first year campus, they have come with a wonderful idea of engineering smart surfaces. I think it's a very interesting topic. When I went through, sorry, I'm outside because of power fluctuation in my house. Yeah, now I'm audible, I believe. So this topic, when I went through the topic, it was really interesting, and it urged my, what I can say, in a sense, to know what exactly it is. So thank you for coining a very nice topic and bringing out such a webinar in this pandemic time. I also congratulate the department for such an initiative and many more to come. I thank the chief guest, Dr. Divya Panchanathan, for sparing her time with us. I hope this webinar is going to throw light on various aspects in mechanical and civil engineering, and also to some extent some interdisciplinary aspects. I request all the participants to be with us till the end and take away the message that is given by the chief guest. So once again, I welcome you all and I thank you for such a wonderful opportunity. Thank you.
Thank you, ma'am. Participants can post their queries. Feedback link will be posted in the chat box of the end of this session. Now, I call Ms. Devi, Assistant Professor, Department of Mechanical Engineering, to introduce our chief guest. Few seconds, ma'am will be joining here. Some technical issues. Yeah, participants can post their queries, and end of the session, feedback link will be posted in the chat box. You will you will not stop learning for the pandemic time also. Yeah,
Yeah.
yeah, it's audible, ma'am.
Yes, yes, sir.
Yeah, ma'am. Yeah, ma'am. Yeah, ma'am. Yeah, I call Miss Devi, Department Assistant Professor, Department of Mechanical Engineering, to brief introduction about our chief guest.
Good evening to all. I'm Devi from Mechanical Engineering Department. First of all, I would like to thank our Dean Ma'am, Dr. N.S. Subhashri, for giving the good opportunity. Thank you, ma'am. It is a great pleasure for me to introduce and welcome the speaker of this startlingly beautiful evening. Good evening to all. Our speakers from the world famous air filtration Donaldson company, the senior research engineer Dr. Divya Panchanathan, USA. Welcome you, ma'am. She's achieved many milestones in her career. I would like to share with you, my dear participants, by this wonderful program. Her research has been published in leading material science journal. She got Gallery of Fluid Motions Award by American Physical Society, and she completed the doctoral dissertations on droplet limitations and underwater plastron restorations using the aerophilic textures from MIT, USA. She is graduate mechanical engineering IIT from Madras, and we are all waiting to gathering the wonderful knowledge about the topic, ma'am. Once again, I welcome you, ma'am. Thank you, sir. I hand over the sessions to sir. Hi, ma'am.
Hel- Hello.
Stage on yours, ma'am. Divya, ma'am.
Yes. Can you hear me clearly? Okay. I'm assuming that you can hear me clearly. First of all, I want to thank the organizing committee for the invitation and for having me here. It's really a great honor to be giving this webinar. and I hope everyone is doing safe during this tough times during the COVID. And with that, I'd like to first start my presentation. I'm just going to share my screen. Hi. Hope you can hear me clearly this time. So today I'm going to be talking about how wettability is an important thing in many applications, and also how we can engineer surfaces to be smart for applications in anti-fouling, hydrophobicity, and drag reduction. So when I say smart, I mean that you give it a property of being able to recover from failure or be active in some way so it enhances its inherent wetting properties. So first, let me show you a few applications where wetting is important in real life. Uh, for example, if you have coffee spill on your shirt, you don't want the coffee to stick to your shirt or wick into your shirt. You just want it to repel and fall off, roll off and fall. And so this is where hydrophobic surfaces are very useful. And when it's a hydrophobic surface, a liquid will not want to wet it, and it will bead up to form an angle that is above 90 degrees, as shown in this right-hand figure. And another application where you want the opposite, that is, you don't want the water to repel, but instead actually completely wet the surface, is, for example, in anti-fogging mirrors or glass. So if you're in your car window on a foggy or rainy day, you see droplets sticking to the window, you cannot see clearly through the window. So for that reason, if you apply a hydrophilic coating, the water will spread completely, and now you can actually see better through the window. So here, in this case, the contact angle is less than 90 degrees. That's where those are hydrophilic surfaces. Something that is relevant in the current times is a face mask, right? So all of us are wearing face masks when we go out. And it's interesting that in these masks, you need to have two types of wettability. On the outer surface, it's important to have a hydrophobic surface so that the water droplets carrying the coronavirus doesn't penetrate the surface. On the other hand, you want to have a hydrophilic surface on the interior part near your mouth so that it captures all the droplets that are coming out of your mouth, and also it helps in wicking all the moisture and keeping yourself dry near your face. So wettability is important in many applications, and not just related to water, but also related to oil. So these include like lubrication, your non-stick pans, filtration, drag reduction, your phone screens where you don't want fingerprints or water to wet it, and also anti-corrosion. So it's important in any place where you have three phases in contact. This could be solid, oil, and air, oil, solid, and water, or water, solid, and air. So as shown by these 3 points in this diagram here. Typically, you have passive coatings or materials applied to give these hydrophobic or oleophobic properties, but then they can easily fail with wear and tear in the actual application. So, which is why my talk is going to be focused on how do you have active methods to improve surface coatings or to recover these coatings from failure. So my talk is going to be divided into 3 parts, which cover the 3 works that of my PhD at MIT, and I'll try to be as brief and clear as possible in these. So as I mentioned in the talk, the Smart, when I say smart interfacial engineering, I mean that we are trying to use active methods to control the wettability of surfaces. So with that, I'll go into the first part of my talk, which is on fouling remediation on oil-water separation membranes. So oil-water separation membranes are important in many applications. For example, in an oil field, you need to treat the wastewater called produced water, which comes out of the oil field, to remove the oil droplets from the water. Also, in cases where you have oil spills in the ocean, you will need to be able to filter the oil out of the water. Typically, these membranes that are used to filter the oil can get fouled over time with the oil, and then you cannot reuse them. So in this talk, I'll be talking to you about a method in which we can use titanium dioxide, a photocatalytic material, to be able to recover the wettability. So this material is special because it is able to have special properties and in the presence of light, particularly UV light. So when you shine UV light on titanium dioxide, it creates electron hole pairs, and this can cause oxidation of organic pollutants that come in contact with it. So this is actually already implemented in applications, for example, on buildings to purify the natural air using natural sunlight. And another interesting property is that under UV light, titanium dioxide becomes extremely hydrophilic or superhydrophilic. So using these two properties of titanium dioxide, we can leverage it to be used in membranes. To generate these coatings, I used a method called layer-by-layer assembly of titanium dioxide nanoparticles. And this is a method which uses electrostatic attraction between nanoparticles and a positively charged polymer to self-assemble these particles onto the surface in a very uniform way. So in this picture here on the left, I show you a glass slide that has been coated with titanium dioxide at the top, but not coated at the bottom. You can see how transparent it is, even though there is a coating of particles on it. And this layer is extremely thin, about 100 nanometers in thickness, and it's very conformal, very uniform. And the right, you can see a mesh, which I'll be using for oil-water separation, that has been coated with the same coating. And you can see how even like non-flat surfaces can be coated very well with this. Then we studied the kinetics of fouling and recovery using contact angle as a probe. So here what I'm showing you is a graph of the water contact angle under oil with respect to time. So what you're seeing is if the water is wetting the surface, which is at time t equal to 0, the contact angle is 0, and also it means that the surface is clean. But as it's fouled, the water doesn't want to wet the surface, and instead the oil wets the surface, shown in red color. Now, if I shine UV light, you will see that the water will start slowly wetting the surface, and it recovers back to its original state. So this takes about few minutes to occur, but you can see how the water drops slowly start spreading on the surface, which means the pollutant is being degraded, and now it's more clean, and so the water wants to wet the surface instead of the oil. Now, in an actual application, what you will see is the opposite. You have oil droplets in water, and so in this case, where I have this membrane or this mesh coated with the titanium dioxide, you can see there is initially the state of the mesh is that is fouled, so the oil is wetting the surface. But as I shine UV light on it, you'll see the oil droplet is actually getting de-wetted, or it is beading up from the surface, and eventually it will leave the surface. So this is very interesting because in an actual application, for example, if you have a membrane underwater that is continuously in use and it's getting fouled, you can radiate UV light on it in situ in the water without removing the membrane, and you can remove the oil from that surface and recover it back to its original state. So here you can see how the oil droplet has completely beaded up and removed from that membrane. So with that, I want to move to the second part of my talk. So I just wanted to give you a short overview of that work. And in this talk, I'll be talking about in this part, I'll be talking about enhancing the superhydrophobicity of a surface through droplet levitation. So, and here, first, I wanted to give you a quick overview of how superhydrophobicity is actually observed in nature. One of the most famous example is the lotus leaf, which all of you are familiar with, where the water droplets don't want to wet the surface of the leaf, but instead it just rolls off immediately. And this property is very unique. And why this occurs is because if you look at the microscale structure of the leaf, you'll see these 1 to 10 micron size bumps that I'm showing in that SEM image over there that are present on the leaf. And they also have a very nanoscale texture that is on top of those bumps. This texture plus a wax coating on this texture is what gives it its superhydrophobic property. So in short, the texture plus the chemistry is important to control the superhydrophobic properties of a surface. You'll see all these other examples like in insects and bird feathers where the similar approach is used. So why is it able to be superhydrophobic? This is because the water droplet doesn't actually sit into the texture, but instead it actually sits on top of the pillars of the the micro pillars. So this means that there is some air that is trapped in the between the droplet and the texture. So it's the air is trapped in the middle of the pores, and so this air is what is helping it be superhydrophobic. Now, if you immerse this same surface under water, you will see a very shiny layer of air that is trapped in the texture. So you can see how this leaf looks very shiny in light. That's because that air is trapped and it's reflecting the light of the surface. And this is what we call plastron in this field. And it's very useful to actually induce a slip of water against the surface, which can help in reducing drag in applications such as ships or other moving vessels in water. You can also reduce corrosion and biofouling because you're actually creating less contact points for the water with the solid. So in this part of the talk, I'm going to be addressing how we can completely eliminate the pinning points of the surface and make it even more mobile or superhydrophobic. So there's a little bit of friction that is still involved with the droplets on the surface because it still has some contact. But if you can completely eliminate all the contact, then the droplet will be more mobile, and you can also have more slip underwater. This effect is actually called the Leidenfrost effect, and it's something that you can observe in your own kitchen. So, for example, if you have a very extremely hot pan in your kitchen and you put a droplet of water on it, for example, your dosa pan, and you put a droplet of water on it, you'll see that the water doesn't wet the surface, but instead, like, it rolls around freely. This is because the water droplet is evaporating at the bottom, close to the surface, and it's creating a thin cushion of vapor that actually insulates the water droplet from the surface. So it's actually now moving friction without any friction on the surface. So this is what we call the Leidenfrost effect. And it has been exploited, for example, to self-propel droplets on ratchet-like surfaces, shown here. And it also can be used for drag reduction because now you have just an air film lubricating the surface. In this talk, so typically evaporation is the way that this effect has been achieved. But in this talk, I'll be showing how we can use this carbonated water, basically a soda water, to do the same thing. So when you open a bottle of soda, you'll see all these bubbles that are coming out of the water. And this is because the pressure is being released, and now the gas is being released from the water. Question is whether you can use this carbon dioxide gas that is being released to levitate the droplets above the solid. So this can be done at room temperature. That's its biggest advantage, unlike the hot pan method that I showed you. And you don't also evaporate the liquid, so you don't lose the liquid in the process. So let's see what's the difference between a regular droplet of water and the carbonated water. So here you see a super hydrophobic surface and a drop of water placed on it. On the left side, you see that there is the droplet is contacting the surface and with a very high contact angle. On the right side, you see a very high contact angle too, but then now you can see there's a very thin layer of air between the surface and the liquid. And you can see how the light is able to pass underneath the droplet. So this is evidence that there is levitation in this case. So in this talk, and this thickness is of the order of about 3 to 5 microns. So in this talk, I'll be telling you now how we studied how long this levitation can be sustained. So as you can imagine, as the drop is degassing, it's not going to be levitating forever. As for example, carbon dioxide is going to be lost over time. So it's a finite time that it's going to levitate, and how long is what we're going to quantify. So first we prepare like transparent hydrophobic surfaces, which allow us to image the droplet bottom clearly. And this is very similar to the titanium dioxide coatings that I showed you, except that now it's made of silica nanoparticles and it has a hydrophobic coating on top of it. And then we use interference imaging to image the bottom of the droplet. So this is the same phenomena that you see, for example, on a rainy day on a rainy day where you see an oil film on water and you see these rainbow patterns that are created. So those rainbow patterns are a result of light interference, and we're using the same phenomena to image the gas layer that is trapped between the water droplet and the surface. So you will see these Newton's rings that are shown in this image on the left if there is gas between the droplet and the surface. So we also quantify the amount of carbon dioxide by using the pH as probe. And here you can see we can control the concentration of carbon dioxide as a function of the pressure we apply to the water. So first, let me show you what happens when you're seeing the droplet from the bottom using the interference imaging method when you deposit a carbonated water droplet. You'll see that as soon as the droplet is deposited, you see these Newton's rings are formed, which is evidence that there is levitation. After some time, however, you will see that after 30 seconds, there is like a pinning occurring at the edge of the droplet. And slowly, there is still gas trapped in the center. The pinning starts moving inward, and finally, the entire droplet wets the surface. So this is like you see like 3 regimes where it transitions from levitation to pinning to complete gassy state. On the other hand, if you just use DI water or regular water, you will not see any of the Newton rings like you saw in the previous video. It just directly goes and sits on the surface as expected. So as I mentioned, in the case of carbon dioxide, you have 3 states: the levitating state, so where the water droplet is not contacting the surface at all. You have the edge pin state, where it's contacting the surface at the edge of the radius, the base. And the final state where it is contacting the surface in the gassy state. So we define the levitation time as the time it takes from the deposition of the droplet to the time it takes to pin on the surface. And we quantify it by using something called the spatial diagrams, where we take like a slice of the video in the center. So for example, you take the diameter and you plot it against time. You will see how the fringes evolve with respect to time in a single figure. So this is very useful for quantifying the levitation time. So as the fringes are going up and down, you can see that the height of the gas layer is changing, and also the pinning is changing. So we quantify the radius of curvature from this diagram here, and we can estimate what the levitation time is. So you can see how the radius of curvature is increasing and then decreasing after a certain point. And that is a point where the pinning actually occurs. And so we can say that that's the time of levitation. So in this graph, it occurs at about 25 seconds. If you do this for multiple droplets at multiple concentrations, and so you have the plot of the time of levitation as a function of the concentration of carbon dioxide here, you can see that the time of levitation increases with the concentration of carbon dioxide. This is intuitive because if you have more concentration of carbon dioxide, you have more gas to degas, and so you have more time for levitation. So there is also, but then the one critical thing is that there is a critical concentration below which there is no levitation. So you need some finite amount of concentration to have any kind of levitation. Below that concentration, you will see like these gas pockets that nucleate, but they don't cause levitation. And below like a concentration about 1 millimolar, you don't see anything happen. It's just like DI water or your regular tap water. So in this work, we have kind of established for the first time the three regimes that are possible with carbonated water for levitation, and we have quantified how they evolve with the concentration of carbon dioxide. With that, I'd like to show you a few useful applications of this effect. So, for example, if you have a superhydrophobic surface and there is a surface defect on the surface, then you will see that just when you have DI water, it would pin at the surface defect, but the soda water will never pin. It will just keep rolling over the surface defect because it doesn't see the surface at all. So the green droplets are the soda water, which rolls over the defect, but the blue droplets, which is DI water, gets pinned at the defect. Another effect is you can use, as I showed in the very first slide, you can use it for self-propelling droplets on asymmetrically textured ratchet-like surfaces. And also, you don't have to pressurize the gas into the water before. What you could do is also generate the gas in situ by using a chemical reaction. For example, sodium bicarbonate and HCl will give you carbon dioxide spontaneously. So if you mix these two droplets, you'll see how there's a spontaneous generation of carbon dioxide, and the droplet actually jumps off the surface and goes into levitating state, as shown in this video. This is what we call on-demand levitation using chemical reaction. Another thing is that you don't just see this only in droplets, you also see it in bulk liquid. So this is an example where I've coated a wine glass on one side, which is on the left side, with the superhydrophobic coating, and on the right side, I have not treated it at all. And you'll see how bubbles are being seen on the right side, while on the left side, you don't see any bubbles. This doesn't mean that there is no gas on the left. It's just that gas is forming an extremely thin layer close to the surface, which is actually helping us not lose any transparency of the surface. So this is very similar to the anti-fogging coatings that I showed you in the very first few slides, except that now it is a bubble underwater. So this is useful in bulk applications also. With that, I'd like to move to the last part of my talk, which is on sustaining superhydrophobicity for drag reduction applications. So underwater applications of superhydrophobic surfaces, as I mentioned earlier, is useful for skin friction reduction, that is drag reduction, in ships or submarines, for example. You can also use it for anti-corrosion and anti-biofouling, because it's reducing the contact between the water and the surface. However, what happens in these applications is that over time, due to pressure fluctuations or due to diffusion, you can lose the air that is trapped in the texture, and the water starts impregnating this texture. In that state, none of the useful properties I mentioned before is possible. So we need to be able to recover the surface in situ, because you cannot remove a ship or a submarine from water whenever you want to recover this. So for that, so this talk is going to address a method to generate gas in situ on the texture and allow it to spread through the texture for recovering it. Previously, a number of methods have been tried. For example, using water splitting to generate hydrogen and oxygen, boiling to generate vapor, and air injection to just inject air into the surface. The main disadvantages is that it requires high energy. You may require high voltages underwater, which is dangerous, and expensive catalysts. And you also require like a lot of mechanical chambers to be built in a ship to be able to inject air uniformly. So in this talk, I'll be showing you a new method, which is using generation gas by using a chemical reaction. So you can, this reaction is decomposition of hydrogen peroxide, which is an unstable compound by itself, and it's found in hair bleach, for example. And so it wants to spontaneously decompose into oxygen and water, but then there is an energy barrier which can be lowered by using a catalyst. For example, you can use manganese dioxide, platinum, catalase, iodide. All these are catalysts for doing this, and then it spontaneously breaks into water and oxygen. This has been used previously in literature to create motion in nanomotors or microtube propulsion. So you coat this catalyst on these nanoparticles or microparticles, and they can generate gas and use it to propel these particles. So in this talk, the idea I'm going to be using is coating a catalyst in the texture so that when I add a reactant, which is hydrogen peroxide, it will spontaneously generate the oxygen gas and it will recover the surface back to its original state. The advantages of this method is that you don't need any electrical energy or electrodes to do this, and the reaction can be self-limited, and there are low-cost catalysts that are available for this. In order to prove the concept, we made these textures on silicon wafer first using lift-off photolithography, and we selectively deposited platinum in between the pillars of the texture, which you can see is about like 50 microns in size. And you can also coat Teflon over it to give it the super hydrophobic property. Then we image the gas in the texture by using total internal reflection method, which is the same thing as this picture I showed you earlier, which is this leaf that has been dipped underwater, and you see this shiny layer of air or plastron. That's the same phenomena that I'm using to image this texture. So for example, on the right, you see this image with bright gold spots and then darker black spots. So the bright gold spots are where the air is present in the texture, and the darker spots are where air is not present. So you want to be able to recover this texture in situ to get to spread the air into the texture. So here now I've added hydrogen peroxide, and you can see how the air is being generated in situ in the texture underwater, and it's also spreading through the texture to recover it back to its original state. So this is really great because now you can do it without removing the texture from the water, and you can see it in situ. But one thing is that it's not possible to do this recovery with all types of texture. Having an optimal texture is crucial to having recovery. In some cases, what you will see is just these bubbles that are formed, but it doesn't spread to the texture. So there are multiple ways in which this gas can wet the texture, and you want to be in the state of plastron, shown on the extreme right, where the air is only within the texture but not above it. So we did some thermodynamic modeling to find out what is the optimal texture for recovery. You can calculate the difference in energy that occurs when you advance the oxygen front through the texture, and this energy difference is due to the interfaces that are created and the interfaces that are destroyed. Then you can replace the texture and the chemistry parameters using the wetting solid fraction, Wenzel roughness, and the Young's equation to obtain an expression for the roughness of the texture as a function of the contact angle. And this will help us design optimal textures for a recovery. So here you can see a texture design map for plastron recovery, where I've plotted my experiments on this as green and red points, where the green points represent where the recovery was favored, the plastron was favored, and the red points show you where blister or where the recovery was not possible. And the line that is dividing the two is the theoretical line that I showed you in the previous slide. So here you can see our experiments agree with our theory, and it's possible to achieve plastron recovery if you have very highly dense pillars and tall pillars. So the more rough your surface is, the better you have recovery. Now, we wanted to demonstrate that this that was proof of concept, but now we want to show that this is possible to recover drag reduction underwater, the property of slip underwater. So for that, we use something called a Taylor Coates cell, where we have a cylindrical rotor that is continuously rotating in a bath of fluid, and you can measure the torque that is required to rotate the cylinder. So if you require more torque, it means you require more, there's more drag on the surface. And if you require less torque, you have less drag. So this is the video on the right showed you how this experiment typically looks. And in order to generate these textures, we needed to take a cylindrical piece of aluminum and then machine it to create these micron scale textures. And then we deposit manganese dioxide to which is the catalyst in this case, and we coat a fluorinated side to give it the hydrophobic property. So now you can see how I've moved from very expensive catalyst platinum to manganese dioxide, which is much cheaper, and this whole method is much more scalable. So if you see, if you measure the drag or the torque, and then I've converted into shear stress as a function of time here, you'll see that initially, when the plastron is present on the surface, that air is present, you have a certain torque. But as soon as you induce wetting, you'll see that the torque increases quickly. And so this means now you have higher drag on the surface. Now, after that, I've introduced hydrogen peroxide, and you can see how the torque recovers back partially during the test. And so we can calculate the percentage recovery by conducting multiple experiments. And we found that you get about 50% recovery, plus or minus 15% over multiple experiments. So the reason you have only partial recovery is because there is some kind of pinning which doesn't allow the air to spread completely to the texture. You can see here an image that is of a rotor that is recovered. And there is like you see shiny parts and you see non-shiny parts. So the shiny parts indicate that there is plastron there, and the non-shiny parts are where there is no air. So you want it to be completely recovered, but it's not able to do it because of pinning defects. So in order to avoid the pinning defects, we made even better textures where we use laser cutting to micro and nano texture this. So you get these nice mountain kind of pillars. And so now you have reduced the contact even further with the water, because you have only tiny points at the tip of the pillars that are contacting instead of the square surface like the previous pillars. And so now this is a video of, you can see how the recovery occurs, and now it's possible to get complete recovery rather than partial recovery. And this method is also more scalable because you can use laser texturing to texture a large scale surface rather than machining. So with that, I'd like to again summarize what I conveyed in this talk. So the main things that I wanted to convey is that you need to engineer surfaces to have the right texture and chemistry to be able to get the best wetting properties. And I showed you how you can use active methods. For example, use titanium dioxide for recovering surfaces from failure, and also using, for example, hydrogen peroxide to generate gas and recover superhydrophobic surfaces from failure. I also showed you how you can use the liquid itself to generate the gas and cause levitation of droplets, and hence enhance the superhydrophobic properties of the surface. So there are multiple ways in which you can smartly engineer surfaces to have some active property and not just be passive. And hopefully there are many applications where this is applicable, and we can further enhance this field by getting cheaper catalysts, finding out what is the best ways to implement these uh, phenomena that I just showed now. I'd like to thank my advisors at MIT, Professor Gareth McKinley and Kripa Varanasi, for giving me a great experience while doing this work, and all of these collaborators who I worked with during my PhD, without whom these works would not have been possible. I also want to thank Dr. NGR University, NGR Educational Research Institute, and Dean N.S. Subashri, and the coordinators, Mr. Saravanan and Mr. Chandar, for inviting me and giving me this opportunity to present my work to this audience. And I really thank all of you for your time and patience. And I hope you learned something from this talk. And I look forward to hearing your questions. Thank you very much.
Yeah, thank you, ma'am. That was a wonderful presentation.
Thank
Now,
you.
I call Mr. Chandar, Assistant Professor, Department of Mechanical Engineering, take over the question and answer session.
Yeah, good evening, Dr. Divya Panchanathan. It's a nice presentation about the smart surfaces for water and oil repellency. So the queries are came. The first queries is how water is formed by decomposition of hydrogen peroxide and stoichiometrically.
So how, if I understand the question, uh, uh, you wanted to know how water is formed by the decomposition of hydrogen peroxide chemically, right?
Yeah, yes.
Okay. Okay. So it's a chemical reaction. Let me see. So hydrogen peroxide is a molecule that is unstable. So yeah, there you go. It's unstable because the bond of water and the oxygen and oxygen bond that is occurs. It's like HOOH. That's how the molecule looks, and that bond between the two oxygens is not very stable. So that's why it's preferable for it to decompose into just H2O and oxygen, which then combines with another oxygen to create oxygen. So but typically it's not spontaneous, in the sense that it takes a long time for it to occur. If you just have a bottle of hydrogen peroxide at room temperature, it would take days for it to decompose. But if you put a catalyst in, that bond will easily get broken in the presence of catalyst. So the bond will go attached to the catalyst, the oxygen will go attached to the catalyst, and it will create this free radicals, which will then break the hydrogen peroxide very easily. I hope that helps answer the question.
Yeah, one more query is there. Hydrogen peroxide can remove scale formation from water.
Yeah, so I have seen this a little bit. It is actually something that is used for what do you call it, disinfecting, or for removing organic contaminants. It is hydrogen peroxide can remove organic contaminants because it creates this free radical HO free radicals, which can go attack like carbon based molecules, and they can form they'll degrade the contaminant. So I think you're right, you can do it. You cannot do it for inorganic scaling. So if you have salt scaling, that's not going to be affected. But if you have some kind of bioscaling, then that can be a help.
Yeah, thank you for your queries and answer. Um, I am hand over to Mr. Saravanan.
Hello everyone, I am Frederick from the Department of Mechanical Engineering. On behalf of Dr. MGR Educational and Research Institute, Chennai, BTech first year, take this privilege to propose a vote of thanks. We all thank our dynamic president, Mr. ACS Arun Kumar, for the encouragement and permission to conduct programs to enlighten the knowledge of us all. We thank Dr. S. Geeta Lakshmi, Vice Chancellor, Dr. V. Cyrilraj, Joint Registrar, Academic and Admin, Dr. D.B. Jebaraj, Joint Registrar, E&S, and all the Deans, HODs for providing various support to host this program. We thank Dr. N.S. Subhashri, Dean, E&S, for the constant efforts to organize and make this international webinar another milestone to success. We thank our speaker, Dr. Divya Panchanathan, Senior Research Engineer, Donaldson Company, USA, for taking special efforts to be with us and inspire with applications, the knowledge on materials, and create a renewed interest on engineering smart surfaces, anti-fouling, hydrophobicity, and drag reduction, sharing the technical marvels to create interested research enthusiasts. We thank all the participants for their keen interest to upgrade their knowledge. Thanks to all the team members for wonderfully creating this international webinar. Thank you.
Thank you, Frederick sir. Thank you all for joining us. We expect the same support for future endeavor. Stay home, stay safe. Thank you to all.
Thank you. Thank you very much.
Thank you, Divya ma'am. Nice presentations today.
Thank you very much for the opportunity.
Thank you.
I'm glad.
Thank you.